Today we're looking at vectors and their 3D applications. So if we have a vector with three components, say vector u as a column vector is written as A, B, and C. This just means this vector is a directed line segment in three-dimensional space. The first component here, A, tells us how our vector is changing in terms of its starting position to its ending position in the x direction. In a 3D plane, the x direction is coming forward or backward. So we can see if we have vector 2i plus 3j plus 5k or column vector 2, 3, 5, this vector moves from the initial point O 2 units forward. The second component B tells you how far across along the y-axis this vector is from its starting position. So for instance, for our vector 2, 3, 5, this vector will move from the origin. Its ending point will be 3 places to the right. The last component C tells us the vertical change from the starting point to the ending point. Now, this is different. Y is no longer the vertical component. For our vector 2i plus 3j plus 5k or 2, 3, 5, we know this vector from the origin is moving 5 units up. And we can see where its location is from starting point to ending point, OP, on this diagram. We can, like usual, change column vectors to component form vectors. So if we have vector u is equal to ABC, in component form, this will be A times I, where I is the unit vector in the x direction. We'll have plus B times J, where J is simply the unit vector in the y direction. And we'll have CK, where K denotes the unit vector in the vertical direction. We add, subtract, and find the length and angles between these vectors, as well as vector projections and resolutes in the same way as usual, except we have 3 components. Note here, you don't normally need to sketch these vectors on a plane with the x, y, and z axis. Here is an example. We have vector C, it is equal to 2j minus 2k. We also have vector D, which is equal to minus 2i plus 2j minus 4k. Both of these in R3, so this just means we're in 3-dimensional space, and that makes sense because our vectors have both k components here. We're going to find the angle between C and D, and we're going to find the vector and scalar resolute of C in the direction of D. Notice before you start that C doesn't appear to have an I component, but that just means its I component is 0. So we write that in. We write C is equal to 0i plus 2j minus 2k. D, we know that was minus 2i plus 2j minus 4k. By putting the 0 in front of the I, you avoid mistakes when it comes to things like the dot product. Let's find the angle between C and D. So like I said, you don't need to sketch them on a 3D plane as such, so you just kind of sketch them anyhow you like. We know that these are position vectors because it doesn't tell you where they start from. So we have vector C from the origin, that will be to the point 0, 2, minus 2. Vector D will be from the origin to the point minus 2, 2, and minus 4. To find the angle between these two vectors, we do the usual. We know that cos theta is equal to C dotted with D, as long as our vectors are both pointing outwards from the angle they create. And then we have this over the lengths of C times the length of D. C dot D, we do the same as usual. multiply each individual components. So for the I components, we have 0 times -2 plus the j components, 2 times 2 plus, this is where it differs from 2D. We're just going to add on the last components multiplied together. So -2 times -4. Again, simplify. C dot D becomes 12. This means the angle between these vectors is acute. To find the length of a vector, in 3D we just do the same thing. Square each component, sum them together and take the square root. So the length of C will be the square root of 0 squared plus 2 squared plus -2 squared. That will give me square root 8 when I simplify, or even better, 2 root 2. The same for the length of D, -2 squared plus 2 squared plus -4 squared. The square root of 4 plus 16, and if we simplify that will be the square root of 24. Again, if you break it down, that will be 2 root 6. This is awesome. We can find the angle. So cos theta is 12 over 2 root 2 times 2 root 6. Simplify the denominator. Hopefully we'll come up with something where we know what theta is. If you rationalize the denominator and simplify it as much as you can, we'll end up with cos theta is equal to 3 root 3 over 6, or just root 3 over 2. And we know what cos theta root 3 over 2 is. Remember that the angle between these vectors is acute, which means that my theta has to be in the first quadrant. So theta would have to be equal to pi on 6. So I've just put up our answers and our different parts of question A. Let's do question B. We're going to find the vector and scalar resolute of C in the direction of D. Because our vector resolute is in the direction of D, that means our vector U, or our parallel component, runs along D. I'll just highlight where I think U will be. Remember, these are position vectors, so put your origin in as well. And we also know we're going to have W, our perpendicular component. Put in your arrows for both U and W. You will start from the origin and go along D until it's directly under C, and then W will go from vector D up to the endpoint of C. Put in the other information. We know that U will be equal to a constant gamma times vector D. And we know that W will be minus U plus C, or if we rearrange this, this will be C minus gamma D. Recall that we can take the dot product D dotted with W is equal to 0. D dotted with W is D dotted with, well, W is C minus alpha times vector D, and that equals 0. U, okay, then we rearrange like normal, and we'll get that gamma is equal to D dot C over D dot D, where we know D dot D is just the length of D squared. Now we have everything we need to find gamma. Luckily, from A we know a lot. we know that C dot D, which is the same thing as D dot C, well, that is equal to 12. We know the length of D, again from part A, that was 2 root 6. That way we know the length of D squared, which is D dot D, is equal to 4 times 6, which equals 24. Therefore, we know that gamma is 12 over 24. Okay, and that just simplifies to a half. This is nice. Therefore, U, our vector resolute, is equal to a half of vector D, or a half times minus 2i plus 2j minus 4k. If you expand that, you can write it as minus I plus j minus 2k. That's our vector resolute. Now we just need to find the scalar resolute, or the directed distance of U in relation to D. We know that U is in the same direction as D because our gamma was positive and it was a half. Therefore, we know the scalar resolute is equal to positive times the length of our vector U. Length of vector U is just minus 1 squared plus 1 squared plus negative 2 all squared from its components. We simplify again and we'll get root 6. Which makes sense because this is indeed half the length of vector D, which had a length of 2 root 6.